This picture is a heating curve. The pause is because as you look at this picture, you might see that it's missing part of the name, the curve part. So in real life, when we get our data, it actually kind of looks a little bit more like that. And then this is a little tiny bit more, depending on the substance. So there is a little bit of a curve to it. However, they decided that it would be clearer to teach students this idea with straight lines. So there you go. Now you have straight lines and we call it a heating curve. So the whole part about heating implies that we're adding heat. You'll notice that that's what the x-axis is about. So you're just adding heat as you go along. And then the temperature is what you're reading, how much heat the substance is at. And so you'll notice right here is this 0, and then around in here is our 100, and that's kind of important. So here's how you want to read the heating curve. If this is the heating curve of water, we all know that water will freeze at 0 degrees Celsius, or you could also say it melts at 0 degrees Celsius. Prior to 0 degrees Celsius, we know that it's ice, and we know that ice can be colder than 0 because, in cold weather, if you go outside and you touch snow and different things, I mean, these things have temperatures that are colder than freezing. So we know that the ice can then warm up to 0, but you don't get ice that just stays ice at like room temperature. It's always a liquid phase. So I'm going to just mention that to get to the liquid phase, you have to actually go through what we call as a phase change. And we already talked about that in the other section about some phase changes. In this direction, so because we're adding heat, we are heading towards adding more heat. In this direction, it's from a solid to a liquid. And when you go from a solid to a liquid, in like colloquial speak, you'll call that melting. But the key word for this chart is that we're calling that fusion, and FUS is the representation of that. So that's key in just a second. Then if you keep adding heat to the ice, once all the ice melts, you're just going to have a cup of water that's a liquid. And if you keep heating it, then it's just going to start getting hot again. So it'll get hot, it'll just keep going hot, but then there's a point at which it's going to turn into a gas. And so once it hits this 100 degrees, the liquid, all the energy goes into converting it into a gas. And so in this direction, we're going from a liquid to a gas. And we call that vaporization, and we use a VAP to represent it. And then this is harder to imagine because when we think of a gas, and maybe you think of like an open container, so the gas starts to float away. So you have to imagine this is like a closed container so that you can still keep heating it once it's a gas. And so, or there's some way to continue to heat it at least to make the gas hotter and hotter. If the gas isn't moving away from the heating source is what I'm saying. And so that gas will start to increase in temperature. So you get those plateaus wherever you go through a phase change. And it takes more energy than you would think to go through a phase change. And you know what a phase change is because you've already seen those pictures about the molecules and how they scooch apart. So this picture right here is a heating curve. The other piece of information you need to know about it is that there are equations that are associated with each of the heating curves or each of the regions. So whenever you're on a diagonal that actually has a temperature change, you actually are going to use an equation you've seen before from General Chemistry 1. So it's in the calorimetry section. It's mass times the specific heat times delta T. And you'll use it here also. And then you'll use it here. So it's all the same formula. The C value that's going to be used is going to be different. So the C value that's used in the first section is this 2.09, and that's for water. Now, if you're dealing with something else, it would have to tell you that you were dealing with something else, and you would have to have your own C value. But for this specific purpose, that is the C value for water. And again, remember that this is actually talking about the diagonal, not the horizontal part. I'll draw a little arrow to make sure that that's clear. The M is mass and delta T is change of temperature. If you are talking about the middle equation, you're talking about water now. And the C value you need to use for that one is the 4.184. And that's the one you're going to be familiar with from GenChem 1. So that's that C value right there that goes in. That's the C value. And then right here is the C value for steam or water vapor. We call it vapor here. So you have to, it's like the same equation, but you have to be particular about which C you put in. And then what about the equations for the other regions? Well, in this flat space right here, Q is equal to N, which is moles, times delta H. And it's specific. It's the delta H of fusion because that's the phase change you're going through. And then up here, this is Q equals N times delta H, but it's delta H of vaporization. And so for water, this is the H for fusion that you're going to be using with that equation. And this is the H of vaporization. So these are still given in the problem, so don't worry about them being given in the problems or that you have to specifically, memorize those numbers. But what you do need to know is that the equations are the same for like whether they're plateauing or in the diagonals, but the constants that are used with the equations change. So the nice thing about having it in this format, though, is that you can identify what region you're in. So let's say it's like, okay, it's a liquid and it's 80 degrees. So you can immediately say, okay, so I'm like here and it goes to 90 degrees. So you can be like, oh, well, then I'm going to use this equation. Or maybe it says that it's a solid and it's going through a phase change. So you know you're going to use that equation. So it's like you can use the picture to help you verify which of those equations you're going to use. So we'll have some examples of those coming up. Last piece of information. This is a heating curve because we are adding heat. You can also remove heat. It's called a cooling curve. You won't see as many of those in this chapter, but just want to make it clear that you can start with steam that's very, very hot and you can cool it. You can go through a phase change that makes the steam turn into water, liquid, and then you can cool that all the way down. And then you can go through another phase change that turns it into a solid, and then you can keep cooling it. It's the same idea. The diagonals will have that same equation in all of those places. And the only difference is that I didn't put a negative, but is that because the energy is being removed, it's the negative form of that equation. And also it's true here on the plateaus. That's Q N times delta H. So hopefully that gets you through the information, understanding how to read a cooling curve as well as a heating curve and the kind of information that you need for a cooling curve if you had to do that, and grab the information from there.